All right, Math372, complex analysis, lecture 29. The goal is to do a lot of the central limit theorem today. And if we start getting to about 5 minutes left, let me know. I want to leave you with a Thanksgiving challenge. It's something I saw from my physics professor freshman year who became my mentor. He said, just in case you're bored at the Thanksgiving table, I want you to have something to think about. And so on the off chance that you are bored during the during the holidays, this will give you something to ponder. All right. I want to first talk about generating functions. I know I initially had said I was only going to do the moment generating function and the characteristic function, but I think I want to do the generating function because it illustrates something nice, and it is a backdoor to something we've already seen this semester. So generating functions. And I'm going to do this just for discrete probability distribution. So, and we had beta tested the camera in terms of where it should be positioned right before class. It's nice to know that as soon as the lecture starts, it no longer works. All right, so let's let x be a discrete random variable on the non-negative integers. This is a little bit restrictive, but not horribly so. If you want to know how many accidents are there, it's going to be a non-negative integer. So there's a lot of counting events that this can describe. And I'm going to let gx of t, or actually no, I guess I use the letter s, be the sum, and goes from 0 to infinity, of the probability that x equals n times s to the n. OK? So this really looks like the expected value of s to the n. If I have two different generating functions, and they are equal term by term, they're clearly the same. Right? What if I just know that that I have two generating functions that are the same, and I don't know that they're equal term by term, but just that they're the same? Is that enough to then deduce that the probabilities are the same? In a discrete case like this, yes. Because let's take s equals 0. And so if s equals 0, then they both have to assign the same probability to 0. Then what you do is you subtract that probability from both sides, divide by s, and then you have a new series. And then set s equal to 0 there. Then subtract that, divide by s, and set s equal to 0 again. So if gx of s equals gy of s in this setup, then the probability x equals n is the same as the probability y equals n. So this is a very nice consequence of these discrete random variables. Let's choose a particularly nice distribution. Let's take a Poisson distribution. How many of you have seen the Poisson distribution? Okay, this is also one way to see who's taking stats classes. So this is one of the more common ones. So we will say x is Poisson with parameter lambda if the probability that x equals n is lambda to the n e to the minus lambda divided by n factorial. And this, of course, is n is in 0, 1, 2. So when I give you something like this, you have to do two quick checks. Is it non-negative? Yep. Does it sum to 1? Yep. And that's what this e to the minus lambda is, the sum of lambda to the n over n factorial. Well, maybe it doesn't always give me non-negative values. What should I assume? So I want non-negative values for the probabilities. Any other assumptions I should make? Yeah, lambda's positive. What if lambda equals 0? Then we have an interpretation game of what does 0 to the 0 mean. Yeah, in this case, it would mean 1. It would be putting all the probability at 1, all the probability at 0, and then every other value of n would have a probability of 0. So let's calculate the generating function of the Poisson process. So gx of s is going to be the sum, n goes from 0 to infinity, the probability it equals n, which will be lambda to the n, e to the minus lambda over n factorial times s to the n. So Arjun, you're on hot standby right now. You're not allowed to volunteer because you've seen this, but your job is to make sure I don't make too many mistakes. Okay? Any thoughts as to how we should evaluate this sum? I'm sorry?
Expand E.
So I could try to expand E. That will give me a double sum. Any thoughts as to how I could evaluate this? I've got a sum over n. So a huge part of math is finding the right way to do the algebra. Which terms want to be together?
Lambda to the n and s to the n.
Yeah, so let's put them together. So sum from 0 to infinity, lambda s to the n over n factorial. And what should I do to the e to the minus lambda? I can just pull that out. What will this sum be? It's just e to the lambda s. So you get e to the negative lambda, e to the lambda s. So this is e to the lambda s minus 1. Now the moment generating function for the Poisson is this the expected value of e to the tx. This was the expected value of s to the x. Oh, I'm sorry. I should have written not n over here. I should have written x. So there's really not that much difference between the generating and the moment generating function. This is e to the tx. This is s. So what should I let s equal? E to the t. So this is just the same as the generating function at e to the t. So it's e to the lambda, e to the t minus 1. What I like about this is we actually have a double exponential. And this is not a cookbook problem that I don't care about, where I just want to see, can you do derivatives and whatnot. This actually occurs in a natural way. Now, since this is the moment generating function, if I would do the Taylor series expansion, I would get the moments. Now, this means I would have to start taking the derivative of this with respect to t. I just want to make a brief remark about a faster way to do the algebra, and then we'll see why we care so much about this. So we have the moment generating function of x was e to the lambda, e to the t minus 1. E to the t minus 1, when I expand, now we'll expand the exponential, the 1's cancel, and I'll get t plus t squared over 2 factorial plus t cubed over 3 factorial plus yada, yada, yada. So the moment generating function is going to be e to the lambda, and I can pull out a t, right? And then I'll have 1 plus t halves plus t squared over 3 factorial plus dot, dot, dot. And so now if I want to expand this, I can now Taylor expand the e again, and I get 1 plus lambda t times this whole crap, t halves plus t cubed over, t squared over 3 factorial, plus the next term, I'll get a lambda squared t squared over 2 factorial, and then this whole crap squared plus lambda cubed t cubed over 3 factorial cubed, and thankfully I have run out of room on the board. If I want to find the first few moments, if I want to find the first and the second moments, I only need to get up to the t squared terms. I don't care about t cubed here. I've already got a t squared here. So I don't actually even need to worry about that. So what's wonderful about this is a way to do Taylor series without doing the differentiation. It's a really nice trick. You just put things in and expand, and then just keep the pieces you need. So what we would get is the moment generating function of t would be 1. The only linear term is going to be lambda t. And then the quadratic term will have a lambda t squared over 2. And then for the next one, we have a lambda squared over 2. So we get that the mean is equal to lambda, which is good. That's the key parameter for the Poisson. It's nice. And then I'll leave it as an exercise for you to figure out what the variance is. And notice that there's a formula relating the variance to the second moment. The expected value of x squared minus the square of the expected value of x is the variance of x. So you can use this to figure out what the variance is of a Poisson. What do you think a Poisson plus a Poisson is? So I take a Poisson random variable, and I take another Poisson random variable, and they're independent. Well, we can go through and we can do the convolution. We talked about how you use convolutions to find probabilities. As a nice exercise, I'm not assigning you problems for this part. I just want you to see what's out there. Actually do the calculation for Poisson plus Poisson. And you can set it up as a convolution. So say xi, well, I'll do xk because this is a complex analysis class, and in a complex analysis class, you should never use I as an index. So let's say we have xk is Poisson with parameter lambda k. Then x1 plus x2 would be the following. So the density, so the probability that x1 plus x2 equals n, so it'll be the sum, n1 goes from 0 to n, and n2 goes from what to what? 0
to n1.
Nope. So I want x1 plus x2 to equal n. If the first one equals n1, what's the range for the second one? I'm sorry? OK. N minus n1, 2. I want their sum to be n. How high can it go? I'm not calculating the probability that's at most n and differentiating. Right? That's how we did it before when we had continuous random variables. We calculated what's the probability you're at most x, and then we differentiated to get the PDF. Now we can't do this. We have a discrete distribution. So what should be the range for n2? I want n1 plus n2 to equal n. Once I tell you what n1 is, how many choices do you have for n2? One choice. n2 goes from n minus n1 to n minus n1. Right? Right? I want to emphasize the difference between the continuous case and the discrete case. Yeah, this is. So there's really no second range here. So what I would just have is the probability that x1 equals n1, which would be lambda 1 to the n1 e to the minus lambda 1 over n1 factorial. And then the second one would be lambda 2 to the n minus n1 e to the negative lambda 2 over n minus n1 factorial. And after you do some algebra, you will get that this is equal to lambda 1 plus lambda 2 to the n e to the minus lambda 1 plus lambda 2 over n factorial. So it's a nice exercise. You can try to see what multiplication by 1 you might need to do. This is the PDF of a Poisson random variable. So Poisson plus Poisson is Poisson. Another faster way to see this, and this is one of the reasons why we care so much, is to use generating functions. So we have the generating function is equal to e to the lambda s minus 1. And we've shown that if you have independent random variables, the generating function or the moment generating function of the sum is the product of the moment generating functions. Since it's just a change of variable, this would also hold in this case. We'll do things for the generating function. We can go back and forth easily. So g x1 plus x2 of t is g x1 of t, g x2 of t. This is going to be e to the lambda 1, e to the t minus 1, e to the lambda 2, e to the t minus 1. So it's e to the lambda 1 plus lambda 2, e to the t minus 1.
Are you using moment generator?
I am. And now I'm going to switch, and now I'll get, oh, sorry, you're right. Oh, these should all be m's. Thank you. And now that I have the moment generating function, I'll pass back to the generating function, and I'll just replace e to the t with s. E to the lambda 1 plus lambda 2 of s minus 1. Remember, at the start of class today, we said for discrete random variables supported on the non-negative integers, the generating function uniquely determines. We know what has this as a generating function, a Poisson with parameter lambda 1 plus lambda 2. Therefore, the sum of two Poissons is a Poisson, and the parameters go exactly as you would expect. One of the things in probability you learn is the expected value of a sum is the sum of the expected values, so the only thing that would make sense would be a Poisson with parameter lambda 1 plus lambda 2. Okay, so what I want to do now is I want to look at a really nice application of the Poisson. And it's going to connect to something we've done earlier this semester, but not significantly earlier. This should be something that's still on your mind. Now, the big result we're leading up to is the central limit theorem. So let's apply the central limit theorem to sums of Poisson random variables. And so I'm going to try just moving this a little bit closer because it does not seem to like things today. All right. So let's go x1 through xn are all Poisson with parameter 1. Wow, that lasted not at all. All right, thank you. All right, so I got to learn to write with my left hand. So x1 through xn are all Poisson with parameter 1. That's fine. Leave it. Okay. So now let's look at x1 plus xn. What kind of distribution is that? It's a Poisson. Be more specific. If you say Professor Miller in my household, that's not enough.
So you're saying 9 is 1?
Yes, I said over here they're all 1. It's Poisson with parameter n, right? All right, so I think it's still in focus at this point, so then we'll deal with that later. Okay? What should this sum be converging to?
Sort of like a Poisson with infinity?
Well, by the central limit theorem,
Normal.
this should be going to a normal. Now the question is which normal? So this should be converging by central limit theorem to a normal. But we haven't standardized things, we haven't normalized things. So it has with mean lambda equals n. And now unfortunately we do need the variance of a Poisson. But the variance of a Poisson with parameter 1 is 1. So we didn't do that calculation, but I left that to you. And with standard deviation, sigma equals n. And I'm using a result from probability that if you have a sum of independent random variables, the variance of the sum is the sum of the variances. I will leave it as an exercise for you to just finish that Taylor calculation. So this is converging to a normal with mean n and variance n. So what is the probability that x1 plus xn equals n? So while you're pondering that, I will keep playing games and I will talk to the tripod, beg it, plead it. You don't have to stay in the closet today if you're good. what is the probability that x1 plus dot 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 plus xn equals n? It's a shame Arjun isn't here. It's the density of the Poisson, right? It's exactly a Poisson. So this is just evaluating the Poisson at n. So it's just n to the n, e to the minus n over n factorial. Because here, lambda equals n. It's just a Poisson process with parameter n. But we know that this is approximately a normal. Now, we have to be careful because this is discrete. The normal is continuous. But that probability, x1 plus xn equals n, should be approximately the integral of the density, square root of 2 pi, and then the variance would be n squared. Oh, no, the variance is n. Sorry, the variance, not the variance, not the standard deviation. The variance is n. 2 pi n e to the minus x minus n squared over 2n dx. Where should I integrate the normal to approximate the probability that the sum is n? From where to where? Any thoughts?
Is it from n minus a half to n plus a half?
Yeah. Right, because we have something that's supported at the integers. So here's n plus 1, here's n minus 1. I should split. And the area under the normal from here, we should basically be putting all that mass at the center. Okay. What result am I leading you towards? I'm leading you towards Stirling's formula. N to the n, e to the minus n, n factorial, right? That's Stirling's formula. What is that supposed to equal? Well, n factorial was supposed to be n to the n, e to the minus n squared of 2 pi n. Oh, look, we've got a square root of 2 pi n. Right? How much does the normal change as we go from n minus a half to n plus f? Oh, gee, let's see. So the maximum change is I put in a 1/2 here, square that, I'll get e to the negative 1/8 n with the n in the denominator. That's essentially 0. And in fact, you can then expand that out and you can see, oh, here's a lower order term of n. So as an exercise, deduce Stirling, n factorial is approximately, n factorial is approximately n to the n, e to the minus n, square root of 2 pi n. And you can even get lower order terms. Now the problem is, of course, we want to be a little bit clear. What do we mean by it converges to a normal? How much is the error? But this is a really nice application of the central limit theorem. You can deduce Stirling's formula from it, and it's another place of seeing where this 2 pi comes from. Okay, so what I want to do now is I want to start proving the central limit theorem. And so I will initially prove it as a complex analysis. And this is what I call that class. Complex analysis to at least justify Stirling's threshold. All right. Thank you. So, proof of central limit theorem by complex analysis. of x1 plus xn. And because this is a relation, if t will be the square root of n. We're calling a linear function x with expected value of e to the tx. Now, this is a hard integral to do. If you could choose what value of t to what value of t would you choose?
0.
Zero. The linear function is always 1. It's always huge because it's an expected value of the Poisson distribution that exists. So if you look at what's going on right now, when we look at the linear function, we have t is c squared down, t is fixed, and it's going to infinity. So we're essentially going to 0. So it should be 1. Well, it's actually close to 1. So we look at this another way, we have the e to the negative square root of n, the y over c of t, and this is x so we're going to get the linear value function of whatever x is at t over c squared root of n to the nth power. Okay? Any thoughts on how to analyze this? To approach for something like this. What do I have here?
Do you want to convert it into a generating function?
Well, it's not a bad thing to try, but
Since mx of 0 is 1, you could expand, you could Taylor expand.
so one possibility is I could Taylor expand this. But then I would have to Taylor expand the original function and raise that to the nth power. Any other thoughts? What kind of expression is this? This is it's a product. This is a class with Professor Miller. Right? What's that? Right? Let's take it. Whenever you see products, there's logarithms. Not instead of having n on the exponent, we're going to have n on the row. Have you done this? Have you done this right for those? So, let's go to the inside. What is n goes to infinity? 1 plus 1 over n to the 1 looks like e to the 1. So this looks like 1 plus 1 over n to the n. And this is 1 minus 1 over n to the n. This piece goes to e over there, so I get e to the n. Where does this piece go to? So it's e over there then. And so what's this product going to go to? And so this product is 1. Okay? That's the math. Math. So we have a heavy limit. And it is, I'm taking this limit, up to infinity, and then up to infinity. How should I do this? There's two ways we can do this.
You know, the telescoping product.
What is a telescoping product?
The factors cancel. So you have 1 plus n.
Yes.
Yeah, if you look at the n plus 1 term,
Well, it is fixed.
n is fixed. Oh, okay. Oh, okay.
strongly urge you to take legs and to really expand. Take legs, rotate and expand. And if you do that, you're going to get the right answer. A lot of people in formulating take partial limits and then take the rest. You've got to be very careful. The best way not to make mistakes like this is to take the logarithm. And if you take the logarithm, you get n squared, which is huge, times 1 over 1 plus 1 over n. So the first term, it's going to be 1 over n. So n squared times 1 over n look like n. But the first term is going to be 1 over n, and that will cancel. So the terms that are going up to the will cancel. And the first thing that's what you're doing is here. The other terms are canceling. But the other terms actually reinforce. Because when you expand minus 1 over n, it's going to have the next term will come out with plus 1 over 2n squared. So returning to what we have over here, this suggests that we should take logarithms. And so we take logarithms, we get greater a logarithmic function. Alright, we get a log squared n log t over sigma plus n times the log of the logarithmic function of t over sigma squared of n. Alright, so this is log squared n log t over sigma. When you're in a book, you can just copy and paste from line to line, which is so much nicer than looking at the blackboard. We're going to take the log of the logarithmic function. Because we have a t over sigma squared of n, the first term of sigma is we have 1, then we have something over 1, something over n, something over n to the 3 halves. Well, if we get to n to the 3 halves, even when you multiply by n, it's not going to have to be present. And because this is convergence, I don't have to worry about that. So I can drop all the t cubed and higher terms. So it's going to be 1 plus the 9 of at t over sigma squared of n plus the second element. Now what's the second element? The second element is the variance plus the 9 squared. Variance is the second element minus 9. I have 2 factorial, and I have a t squared over sigma squared n plus higher order terms that I don't care about. And now I expand the log. And so this is going to be log squared of n log t over sigma plus n. Okay, here we go. So I'm plus blah. The first term is blah. The next term is minus blah squared over 2. So the first term is going to be log t over sigma squared of n plus sigma squared plus n squared over 2 factorial, which is also known as 2, t squared over sigma squared n plus higher terms that I don't care about. The next one is going to be minus 1/2 the square of blah. What's the other part of the square of blah?
The square of the left part, mt over sigma.
T over sigma n. Right.
Yeah.
Because what's going to be a t cubed term, and then n over 3 halves, if this is itself, it's an n squared to the rest. So all that means is, okay, 1 squared, t squared over sigma squared n plus higher order terms. Alright, this is where I'm pretty that a lot of mistakes have happened. When t over sigma, that cancels that. Okay. 1 squared over 2, t squared over sigma squared n, and t squared over 2 sigma squared will cancel. And so I'm left with sigma squared t squared over 2 sigma squared n. The sigma squareds cancel, the n squareds cancel, and I'm left with t squared over 2. And therefore, the Riemann function of z is converted to e to the t squared over 2. There's several types of conversions you can go to. I'm not going to want to go into that now.
function is essentially the Fourier transform. Where the kappa in the Fourier transform is standard normal. And so this is actually the standard normal. So this is the round linear function on the standard normal. So we have this calculation is in 3 different ways. So what I've just shown is that the linear general function corresponds to the linear function of the standard normal. Now all we need to do is invert. And so this is converting to the linear general function of the standard normal. The systems themselves must be converging. And that's the hard part. That's the part that's going to require complex analysis. The proof that we have is accumulation points. It's not that I was generating which is some additional things, but it's a nice proof. The next question to ask, and we've still got a little time before Thanksgiving, that's good. The next question to ask is, I was surprised about the central limit theorem. What's the same result in complex analysis, which we're not going to get to? But this is incredible universality. I don't know very much about linear variables. It's wrong, I want a linear general function to exist, so I can't have a minus growing too fast, but most of the Poisson distributions I look at will satisfy that. Some of the question are not, but most of them will. So the question is, why do we have this great universality? So the first thing is, let's look at the assumptions. How strong are the assumptions that to say 1 must be 0? Okay, so let's not a bad assumption. So this is shift, right? Let's say this goes into the shift happens. Just shift it so that it will be 0. The same thing in physics, right? How to say potential energy of 0 is. Is it at the sun? Is it at the floor? Is it at the blackboard? Or at the center of Earth? It's still at the lambda. All it means is differences in potential energy. So we need to adjust our system so that the limit is 0. The limit assumption. So of course the limit exists. The next assumption is that the variance to be 1. Is that a big assumption? Just scale. So the symbols that stick with me, this is, wow, over 20 years ago, I was in a high school physics class, and we had conversion tables in the back of the book. And one of the conversion factors was from fermions per fortnight to minutes per second. So if you should really how fast something is moving in fermions per fortnight, I could convert. Can you use fermions per fortnight? Yes. When you look at these small construction projects, fermions per fortnight also makes sense as a real impairment. It's just a conversion. If there's a minutes, there's a minutes in feet or inches. Doesn't matter. So the system that radius to be 1 is not a big deal. So variance exists. So here's what's happening. We have this entire island, and this is the high point of this proof. The higher values surface in the main term. They only surface in the error term. So we actually keep track of the higher order terms. Well, the error terms are equal to t squared over 2. And the first thing that will appear is the third element. Once the solution is symmetric of the positive, the third element vanishes, so the first thing to appear will be the fourth moment. And so the reason is the higher limits affect the rate of convergence to the Gaussian. But the Gaussian is the universal result because the main term is independent of the shape of the distribution. That's wonderful. It is limited what distribution we're working with. How quickly? So now we've taken stats. So this is a 30 points is enough to be reasonably confident. I don't know if the pathways of the business with 30 points won't work, but most of the ones we can find is perfectly fine. It really comes down to the higher limits as to how fast things are going. So this is a true mathematics. This is one of the results in mathematics. And then unfortunately, it all comes down now to just one little factor in the way, but we can also afford after Thanksgiving. Alright. So now it's time to let's see what the plan is for Thanksgiving. So, my physics professor, Frank, truly wonderful. I had him for, I think, 3 years, quite analysis. Physics eventually went out into unit theory because he was sick and tired of having so few data points to work with. In unit physics, if you got 100 to 1,000 data points, that was huge. And the initial values of quantum elements. As soon as he was talking about now, in a math class, it'll take 6 weeks to justify this interchange. Physicist works. I don't think I can find this. So I'm going to define an operator for you. I'm going to define this symbol, which is very similar to symbols you've seen before. I've seen this before. So define the integral of f to by the integral of t goes from 0 to x of f of t dt. I think that's how I want to do it. Okay. So I'm going to solve the integral of f equals f minus 1. Okay? All right. So let's see if we do it. All right, thank you. All right. So here we go. The integral of f equals f minus 1. This is the same as f minus integral of f equals 1. This is the same as 1 minus the integral of f minus f equals 1.
Divide by 1 minus the integral.
So f
Equals 1 minus integral inverse acting on 1. All right, now what should I do? You're joking, right? All right, let's do a geometric series. All right, 1 plus integral plus integral integral plus integral 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 plus. Okay. Now what do you want to do? Yeah, sure. I mean, we don't really care what we're sure. So f is now equal to 1 plus the integral of 1 plus integral integral of 1 plus integral 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 of 1 plus dot dot dot. All right, well, let's look and see what we've defined. Integral is integrate your function from 0 to x. So the integral of 1 means the integral from 0 to x of dt, which is x. So f of x is 1 plus x. Now we need integral integral of 1. Well, the integral of 1 is x. So now we integrate our function. So that means integrate from 0 to x of t dt. And what will that be? X squared over 2. Is that really how you want to say it? Thank you. What will the next term be? And this function is also known as? And if you plug in e to the x, if I integrate e to the t, I will get e to the x minus e to the 0. E to the 0 is 1. So yes. So now we could put like stars by all the illegal steps or the steps that we are concerned about. I'd say this one gets a star. I'd say this one gets a star. I'd probably give this one a star as well. This one's actually okay. This one's okay. That's just subtraction. This is just, so, you know, there's a small little part in the middle where things are a little bit concerning. Is this valid? Can this be made valid? Can this be made rigorous? What space of functions can you define this integral on? And we now have an operator. When does this operator have an inverse? When is that inverse given by the series expansion? When can you then justify expanding like this? So I really wanted to do this because, you know, one, I was pretty sure we'd have a couple of minutes at the end of the class today, so this is a really good time to do it. And two, I have told you so many times, okay, and now of course the justification is the standard justification and everything is fine and we can interchange the operations. I want you to see at least one situation where it is not as clear how to make this rigorous. What space of functions are we looking at where this is valid? This is how you tell a good physicist. They have a great instinct. And again, I don't know who is the one who created this problem. I will email him and ask him if he remembers. You have a great instinct as to how to work with the mathematics and play with it. And then you come in and you say, well, if we restrict our functions to the following space, we probably want some kind of notion of a norm. And so if I have a norm for this operator, maybe what would you want that norm of that operator to be? I'm not even saying what the norm is, okay? What would you want to know about the norm of this operator, the integral operator? There's something you probably want to be true about the norm of that operator. Be more specific or be more finite. How finite? I'm sorry? You could pick one. What do you mean by pick one?
Have the norm
be one?
if it's a value, yeah.
Would you want? So when you look at this, I claim that there's a step that gives you some idea of how large you want the operator norm to be. Which step do you think? You got 3 illegal steps to choose from. Less than 1. Excellent. Why do you want it less than 1?
So that the 1 minus
Yeah, so that we can expand. So maybe if we can somehow restrict to a space of functions where there's an operator norm and that norm is less than 1, then the inverse will actually be this. And maybe there is a hope to justify this and have this make sense. So as you're stuck in airports, as you're traveling, as you're hearing family stories for the nth time that you have heard already sufficiently many times, here is something for you to be thinking about. I will let the other people give you other types of food. This is the food for thought.